Welcome to all. Today we will understand how to draw layout diagrams for a MOS transistor, and then we will go to construct and simulate for a logic gate. Why we want design rules? The reason is fabrication process needs different masks, and these masks were prepared from layout. That is the basic reason. And second reason is layout is an interface between circuit designer and fabrication engineer. Circuit engineer may be considered as a front-end engineer, and fabrication engineer may be considered as a back-end engineer. So it is an interface between both of them, so it has been followed. The third reason is it contains some set of rules to be followed to draw the layout diagrams, and it is the design rules which allow the translation from stick diagram to layout diagram. Stick diagram doesn't follow any rules. It is nothing but it is color convention which is being followed. Suppose if you want P diffusion, you go for yellow color to represent P diffusion. If you want to represent NMOS transistor, you go for N diffusion, which is going to be green color. Metal lines are being drawn with blue lines, and then the contacts have been drawn with X mark or dot, which is represented in black color, and the polysilicon has been represented in red color. So this translation stick diagram is simple way. Using color pencil you can draw it. This transition there should be method, and this design rules will be helpful in moving from stick diagram to layout diagram, and it specifies minimum allowable line widths for physical objects on the chips. These are the reasons why we are going for design rules. So if you go for layout design rules, we have micron rules and lambda based design rules. So if you go with micron rules, all the dimensions are being expressed in terms of absolute dimension, which is micrometer or nanometer, and these rules will not support any scaling in the sense, suppose if you want to reduce the length, you cannot go with, if you work with micron rule, there is no support for scaling. Suppose if you work with lambda based design rule, which has been developed by Carver, Med and Conway, so all dimensions are expressed in terms of scalable parameter, which is called lambda, right? And if what is lambda? Lambda is minimum length by 2. What is length? If you draw the MOSFET, the distance between source and drain is going to be considered as length. So this length by 2 is nothing but lambda. Or what is length? Length is 2 lambda. So the benefit of working with lambda based design rule is it will support scaling. Suppose if you are working today, if you we may be working in 90 nanometer, that is the length between source and drain. Suppose if after 2 years or so, the dimensions may go up to 7 nanometer or 11 nanometer. Today we are working with 11 nanometer. So if that is the case, then we doesn't have to redraw it when you follow lambda based design rule. So lambda based design rule, which is scalable CMOS design rule, defines scalable rule based on lambda. Lambda is nothing but half of minimum channel length. So what is stick diagram? Stick diagram is, we have seen stick diagram. Stick diagram is a draft of a real layout. It serves as an abstract view between schematic and layout. And we have seen this lambda. Lambda is nothing but half of transistor length. These are the rules to be followed. So the first rule is metal and diffusion have minimum width and spacing of 4 lambda. First rule. Second rule is contacts are 2 lambda cross 2 lambda and must be surrounded by 1 lambda on layers above and below. Polysilicon uses a width of 2 lambda. When we go for gate, we will use polysilicon. It should have a minimum width of 2 lambda. Poly overlap diffusion by 2 lambda where a transistor is desired and has a spacing of 1 lambda away where no transistor is desired. So this will differentiate where there is a transistor and there is no transistor. Polysilicon and contact have a spacing of 3 lambda from other polysilicon or contact, and N-well should surround PMOS transistor by 6 lambda and avoid NMOS transistor by 6 lambda. Right. These are the rules to be followed when you work with CMOS circuit. So when you consider CMOS, I said it will contain both PMOS and NMOS. So this is P substrate. We can have N plus diffusion, and here you can have N plus diffusion. I could consider this as my source and this as my drain. So in the same P substrate, we want to fabricate P MOSFET. This is N. We want to fabricate P MOSFET. If that is the case, work with a well which is called N material well, N well. So inside N well you can have P diffusion, which is going to act as source, and this is going to act as, this P plus is going to act as drain. So in between source and drain, normally you will have gate, and this is nothing but gate. So this layer is nothing but SiO2 layer. So in a single substrate you can fabricate PMOS and NMOS, and that is called as CMOS, which is PMOS plus NMOS. So wire tracks is the space required for a wire. So 4 lambda is the width. So 4 lambda is the width of the wire track, and there should be a space between next track, it should be 4 lambda. So totally you need 8 lambda for laying a single wire. So transistor also consumes one wire track. Suppose if you take this is going to act as my whatever it may be, symmetrical device. MOSFET is a symmetrical, you can change source as drain or drain as source, because if you take here it is N plus and this is also N plus, you can change source and drain. If you consider this, here it is source and this is nothing but my drain. So if you consider this, you need 4 lambda. Transistor also consumes one wire track, so we need a track, so it is going to be 4 lambda, which is to be present between source and drain. Okay. Well spacing. So as I said, if you want P MOSFET, you inside P substrate you should put N well. So a well must surround a transistor by 6 lambda, implies 12 lambda between opposite transistor. In the sense, there should be a distance of separation of 12 lambda between PMOS and NMOS, and this distance will give a room for one wire track. That is what is the meaning here. So we will understand this by simulating an AND gate. So we have to start with pull-up network, P diffusion. We are going to construct a 2-input NAND gate. So we need a single transistor will need 12 lambda width. So I need to fabricate, or I need to take up 2 transistors. So what I do is I am going to take 24 lambda, 24 lambda, and width is 4 lambda. Length is 24 lambda. Similarly, I want N diffusion. The P diffusion and N diffusion should be separated by 12 lambda. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here we will start the N diffusion. Okay. Make P contact. So this is my P contact. Similarly this end you make, and the middle you have, in both sides we have 4 lambda. Okay, then you need n contacts. So n contacts, check for the design rule whether the design rules have been satisfied. No design rule errors, so you can proceed. We need to so this green is nothing but here we are going to have pull down network, above you are going to have pull up network. So pull up in the sense you need an n well, so go for n well, and the space is 1 2 3 4 5 6 lambda should be the space which should be free. So 1 2 3 4 5 6. Okay, so you need more, you need to give minimum 6 lambda space between PMOS and NMOS. So that is the case 3 above. Yeah, check for design rules whether design rules have been, yeah, we have to, in this space you have only 5 lambda, here you have to give 1 lambda space again, so go for n well. Now give this. Okay, or otherwise we should delete this. 1 2 3 4 5 6. Okay, check for design rules. So now there is no design rules. So this side you have 6 lambda, this side you have 6 lambda, this side you have 6 lambda, and this side you have 6 lambda. Now the n well should be connected with most positive potential, so give VDD supply to this n well. So you should connect the source of the P MOSFET to the VDD. So two input or two PMOS is there, so two PMOS source has been connected to drain. Okay, then we need poly. So poly 3 lambda above this, and width should be minimum 2 lambda. So we have more room. So this is my first MOSFET. Second MOSFET, I have to draw another yes. So this is VDD and this is VDD. So this is source of one P MOSFET and this is the source of another P MOSFET, and drain, this is nothing but the drain of the each MOSFET which has been diffused. So this drain is going to be considered of the drain of the two PMOS transistor. So in bit we have to give, or we have to take the output. So take a metal line. So can also draw. Okay, so minimum 4 lambda should be there space. So okay, So we need to give inputs. Add a clock, give it as A, add a clock to second input B. This blue metal line is going to be my output, so make this as visible. So this is going to be your Y. You can check design rule by completing each step. So go for design rule. Design rule has been detected. Okay, the polysum dip is less than 3 lambda, so it should be above 3 lambda, but here it is only 2 lambda. So go for poly now. Put a lambda extra here, and okay, now go for design rules check. Yeah, it doesn't have any error. Now you have to simulate this. Yeah, so this is nothing but the input, and this is nothing but your output, and Y is nothing but your output. So this is how you have to follow the design rules. So this says that this 12 lambda is nothing but the distance between P diffusion and N diffusion. So in between that you can have a metal layer which is of 4 lambda. This metal layer should have 4 lambda spacing between P diffusion and N diffusion. If you see this, this metal is nothing but 4 lambda, and this P N diffusion, if you take 1, 2, 3, 4 lambda spacing should be there. So we have maintained the design rules. Each step you can check this design rule checker, that will say whether your design contain any error or not, right? This is the true table where we get the output when both the inputs are equal to 1, Y will be equal to 0. And with this we'll end this. Thank you all.